is the summer of 1930 on the steamship Lloyd Triestino sailing from Bombay to Venice. A 19-year-old physics student from Madras is doing calculations in the ship's cabin, combining special relativity with the new quantum statistics. The conclusion he reaches will rewrite the death of every star above 1.4 solar masses, and his elder colleague at Cambridge will publicly ridicule the result for the next 4 years. Tonight, we cover the Chandrasekhar limit. Joining me are a theoretical astrophysicist and a stellar astronomer.
A white dwarf is what remains when a star of less than 8 solar masses exhausts its nuclear fuel. The outer layers are blown off in a planetary nebula. The inner core contracts to roughly Earth size, and the star is now supported not by thermal pressure but by electron degeneracy pressure, a purely quantum mechanical effect arising from the Pauli exclusion principle. The Pauli principle prohibits two electrons from occupying the same quantum state, and at high enough density, the electrons push back on gravity. The white dwarf is one Earth radius containing one solar mass.
On the steamship voyage, the 19-year-old student noticed that electron degeneracy pressure is bounded above. At sufficiently high densities, the electrons become relativistic, their velocities approach the speed of light, and the equation of state softens. Pressure no longer rises fast enough with density to support increasing mass. He calculated the critical maximum mass beyond which the white dwarf cannot resist gravity. The answer is approximately 1.44 solar masses. The exact value depends weakly on chemical composition. Above the limit, the star must collapse.
The formula carries the three fundamental constants of physics. The Chandrasekhar mass equals roughly omega times h bar c divided by big G all raised to the 3/2 power divided by the proton mass squared, where omega is a dimensionless number close to 2. Three constants, Planck, h bar, the speed of light c, and Newton's gravitational constant G, combine to give a stellar mass limit. This was the first time in physics that a macroscopic astrophysical observable was directly built from the three fundamental constants of nature. The result was deeply controversial.
In 1935, the Royal Astronomical Society held a meeting where a much more senior astronomer publicly ridiculed the calculation. He argued the relativistic degeneracy result must be wrong because the conclusion, that massive stars must collapse to a singularity, was absurd. The young Indian student's career nearly ended. He moved permanently to the United States and never worked on stellar structure again. The community took 30 years to accept the result. The Nobel Prize in Physics finally came in 1983 for that calculation done on the ship at age 19.
Above 1.44 solar masses, the white dwarf is unstable. If the mass is between approximately 1.44 and 3 solar masses, the collapse halts at the nuclear density and a neutron star forms. Above approximately 3 solar masses, no known force resists gravity and the collapse continues to a black hole. The Chandrasekhar mass therefore marks the boundary between two distinct stellar remnant fates. Every observable property of every collapsed object, every pulsar, every X-ray binary, every gravitational wave merger detected by LIGO depends on this 1930 calculation.
There is one more spectacular consequence. A white dwarf in a binary system can accrete matter from a companion and slowly climb toward the limit. The instant the mass crosses 1.44, runaway thermonuclear ignition of the carbon-oxygen core destroys the entire star in a Type 1a supernova. Because the ignition mass is essentially fixed by the Chandrasekhar limit, every Type 1a supernova reaches almost the same peak brightness. They are the standard candles of cosmology, and they are how the accelerating expansion of the universe was discovered in 1998.
The limit is also tested directly. The Hubble Space Telescope and the Gaia Space Astrometry mission have measured masses and radii of hundreds of white dwarfs across the Milky Way galaxy. Every measured white dwarf sits below 1.44 solar masses. No exception has ever been found. The agreement with the 1930 calculation is at the 1% level. The Chandrasekhar limit is one of the rare results in physics where a quantum mechanical calculation predicts a precise astronomical observable that is measured every day.
3 takeaways. First, the Chandrasekhar limit is the maximum mass of a white dwarf, approximately 1.44 solar masses, derived by a 19-year-old student on a steamship in 1930 from special relativity plus electron degeneracy pressure. Second, above the limit, electron degeneracy fails, and the star collapses to either a neutron star or a black hole. Third, Type 1a supernovae result from white dwarfs reaching the limit and are the standard candles that discovered the accelerating expansion of the universe in 1998. Thank you, theorist. Thank you, observer.